Section 9.2, inner product. And Fourier series are application of this inner product space. Okay. In this section, we generalize the Euclidean inner product on Rn, which was considered as a dot product, to introduce the concept of length, distance, and orthogonality in a general vector space. Okay? Yeah, we generalize the Euclidean inner product concept to a general vector space. Inner product and inner product space. Inner product on real vector space V, real vector space, is a function assigning a pair of vectors uv to a scalar inner product of u and v like this, satisfying the following conditions. 4 conditions. You know it. You have seen this before with the same notations. It's commutative, and it can be disputed, and scalar can come out, and it's always non-negative. And if inner product is equal to 0, then u should be a 0 vector for every u in V. These 4 properties, same properties for the dot product, that Euclidean inner product that you have seen in earlier chapters. If a vector space has an inner product, this kind of operation, then we call this vector space form an inner product space with this inner product. Vector space form an inner product space with this inner product defined. Okay? If we have an inner product that satisfies these 4 properties, if vector space has that inner product, then we call that vector space with this inner product form an inner product space. Here, Euclidean inner product, the dot, which is a dot product, is an example of an inner product on Rn. Okay, now, let's think about how other inner products on Rn are possible. For example, consider a matrix A, n by n matrix A, and let U and V be the column vectors of Rn. Then if we define inner product U and V like this, like U and V, inner product U and V like this. V transpose AU like this. Sometimes we write it as a inner product of U and V with a matrix A. Okay? So this, if we define this, inner product like this, then let us find the condition on the matrix A so that this function becomes an inner product. Okay, when this satisfies 4 properties to become an inner product. When? Think about this. In order to be an inner product, this operation should satisfy 4 conditions. Okay? And first condition should satisfy. First conditions. First condition. We consider the conditions 2 and 3. This condition. This can be written as W transpose times A times U plus V. This can be splitted like this. So this can be written as inner product of U and W plus inner product of U and V and W. And when you have a scalar, then V transpose A times CU, and C is a scalar, so it can come out. So, and this is the inner product of U and V, so C times inner product. So these 2 properties satisfies without any difficulties. Easy. Then we have 2 properties left. First condition. Okay. V transpose AU is an 1-by-1 matrix. It's a scalar. Okay. It's just real number. The transpose of V transpose AU transpose is V transpose AU. So inner product of U and V is equal to V transpose AU. So this is 1-by-1 scalar. So it's same as transpose. So this can be written as U transpose A transpose V is equal to U transpose AV, which is the inner product of V and U. But in order to satisfy this, what we should have? we should have A transpose and A is same. This is this. This is that. So if we want to have this and this same, then this should be same. In order to be same, A transpose same should be as A. If not, this may not be same. Okay? So, in order to have this first property satisfied, we must have A is equal to A transpose. So if A is a symmetric matrix, then it always satisfies first condition as well. Next. Okay. If A is a symmetric matrix, then first condition is okay. So we only need to check fourth condition now. M by N symmetric matrix F satisfies this for every non-zero vectors. Okay. So, okay, this condition. So we should have this this U transpose A V is always non-negative, and particularly is positive for any non-zero vector U. Okay, this condition should satisfy. Then when this condition satisfies, this condition means that A is positive definite. Okay? In other words, if A is positive definite, then this inner product of U and V, which is V transpose A U, which is always positive, and if it is equal to 0, then U should be equal to U and V should be 0. Okay. So A is positive definite. You have learned this concept of positive definiteness in chapter 7. Okay. So therefore, to level, if A is an M by N symmetric matrix and positive definite matrix, then this operation satisfies four properties of inner product always. So the well-known Euclidean inner product space is the special case of this inner product when A is equal to identity matrix, which is symmetric and positive definite. Okay. So inner product, Euclidean inner product is a special case of general inner product, okay, which can be defined when the matrix A is a symmetric positive definite matrix. Okay, for any non-zero vector U, if eigenvalues of A are positive, then it always this. You have learned this. If every eigenvalues of A are positive, then that matrix is positive definite. So to check positive definiteness, all you have to do is just find the eigenvalues of A. Okay, if they are all positive, then X U transpose A U are always positive. Depend on the eigenvalue. That's why we have learned quadratic forms. Next, if A is a 2 by 2 matrix, which is symmetric, then the UVs are arbitrary vectors in R2, then inner product of U and V, which is defined as V transpose AU, then this satisfies all the conditions of inner product. Okay? And now let us show the A is positive definite. Okay? Just find the eigenvalues of this matrix A. Then they are both positive. So it's positive definite. So it is symmetric and positive definite. So that satisfies four properties of inner product. Okay? So that forms an inner product. So this is another inner product which is not same as Euclidean inner product. Okay? So we can define many different inner products with many different symmetric positive definite matrix A. Norms and angle. If let V be a vector space with an inner product of U and V, the norm or length of a vector U defined as square root of inner product of U and U. Like before, angle between two non-zero vectors U and V is defined samely like this, using the inner product. And norms follow from the inner product. Okay, so the same angle definition for the angles and norms. And two vectors is called orthogonal if the inner product is equal to 0. For example, if we have a matrix vector U with respect to the inner product this, okay, then the norm of this vector U is the square root of 43, and but if we use the Euclidean inner product, then this norm is defined in this way, which is the square root of 10. So if we use a different inner product, then the norms and angles could be different, like you see here. And for any inner product space, the triangle inequality hold. Using the Gram-Schmidt orthogonality process, we can always find the orthogonal and orthonormal vectors from a given linear independent vectors by using this inner product. Now, for the same Gram-Schmidt orthonormalization process, but we can now use the general inner product instead of the dot product that you have used. Next, inner product on complex vector space. Okay, if let V be a complex vector space instead of linear vector space, and V U W V any vectors in V, and C is from complex number via any scalar, then function from this to C is called an inner product space, inner product or Hermitian inner product. If this operation, this function satisfies the following four properties. Everything's the same except its conjugate. Okay, since we are using the complex number, we are using conjugate here. If it satisfies these four properties, then we call it is a inner. We call it the inner product on a complex vector space, or Hermitian inner product on a complex vector space V. Okay. Same thing with this complex. Complex vector space with an inner product is called a complex inner product space or a unitary space. Okay, unitary space. To make a distinction, if the inner product is equal to 0, then we call those two vectors are orthogonal, and the same properties satisfies except what? Except these are same. When you have inner product like this, then this C comes out with conjugate, because we defined what? U the inner product U and CV can be defined as conjugate transpose of CU, CV times A times U. Okay? Here, this can be written as C conjugate times V, conjugate transpose times AU. And here, this is the inner product of U and V, so this C conjugate should have. So only difference is if C is on the back, then when you come out with the conjugate transpose, okay? That's, when you're dealing with complex numbers, this is the only difference. So if U and V's are vectors in Cn, then Euclidean inner product for vectors in Cn can be defined in this way. This is just like an inner product of U and V, okay? Conjugate transpose. V star times U, okay? V star times U. This satisfies all the conditions for the inner product space, for the complex vector space. Continuous functions on AV to C, complex set C, set of continuous functions. If we can define two, we can choose two vectors from this continuous function, this set of vector space. Okay? Then if we define a vector addition and scalar multiplication like this, then this form a complex vector space with these two operations. This satisfies two basic properties and 8 operational properties. So this form a vector space with these two operations. So this form of vector space. In this case, these are these are where it is. These are in C. So these are complex. These can be complex numbers. So we can write the imaginary part, real part, and complex part, and separate. And by addition, those two parts, we can define the f of x like this. Same for f and t. When f1 and f2, little f1 and f2 are continuous functions from a, b to r. These are real and these are reals. So when you multiply imaginary number here, this can represent all the imaginary numbers. So as an image of capital bold F. Okay. So with this setting, we can define an inner product like this, Inner product of bold F and G is an integral from A to B the conjugate of g of x times f of x times dx. Okay? Then this form four properties of inner product space, inner product. So this form inner product space. It satisfies all the four properties. Okay? So we have checked the condition for C. So we can define, we can check the conditions. And we now here to show the condition 4. Let's see. Inner product of these two can be written as this, which is this is a complex numbers, so we can define as a modulus squares like this. Then this is always non-negative, and this is non-negative. And if this is equal to 0, then f of x should be 0, like this. So it satisfies fourth property as well. It's always non-negative. If it is equal to 0, then that f of x should be a 0 function. So it satisfies all the four properties of inner product space, inner product. So this form of inner product space. This is very important. Now we have a complex inner product space on the complex functions. Okay. From those, we can define norms and distance. Norms get defined similarly, distance defined similarly, like what we did before. Okay. So, for example, we have two vectors in C2. And then we can define the Euclidean inner product of these two vectors like this, and Euclidean distance on this. Okay? From the definition. If we have a function, complex function like this, f of x, we can define the norm of f of x. Norm of f like this. Okay? And which is what? Norm of this is inner product, square root of f of the inner product of f of x and f of x, which can be written as this. This conjugate is minus, so these are cancelled. So integral from 0 to 5, 1 dx is pi, square root of pi is the answer. So norm of this continuous function is square root of pi. That's it. Cauchy-Schwarz inequalities. Here. For any vectors in a complex inner product space V, for any vectors satisfy this Cauchy-Schwarz inequality like before. The proofs are exactly the same. Triangle inequalities just follow from the Cauchy-Schwarz inequalities. Same thing. If v is equal to 0, u is equal to 0, then it's trivially true. If u is not 0, then we can think about projection of v onto the span of u, and w is a span. So when we have a u and v, then we can think of projection of u onto projection of v onto u, which is p, which is t times u, and then we can find w as v minus p, which is also gonal to u. And from here, from the property of inner product, the inner product of w and w is always bigger than 0, which can be written as this, which can be splitted as this, and here p here, and w and p is orthogonal, so it's a 0 vector, so we only have this term. And here, w can be written as v minus p, so this can be splitted in this way. And p can be written as tu, so that can, and t can come out like this. So we have this property, this one, which can be written as this. From here, if we move this and multiply the square of norm of 2, then we have this. This is the product of these two, which can be written as a square of the modulus of inner product of u and v. This gives us what? Square root of this gives us Cauchy-Schwarz inequality, like what we had before. This is very important. U and v here, that is, if you find the norms, and then you can easily check that satisfies Cauchy-Schwarz inequalities. If we have two vectors here, and you can easily check these values and these values to see the Cauchy-Schwarz inequality hold for any vectors in complex inner product space. That works. The Cauchy-Schwarz inequality has a power to give us many important facts. If we define the inner product differently, then for that inner product, that this Cauchy-Schwarz inequality hold. So this inequality should hold. If we define an inner product with these integrals, then it also holds the Cauchy inequality. So this inequality should hold for the given inner product. So the triangle, for same thing for the triangle inequality. Triangle inequality just follow from the Cauchy-Schwarz inequality, as you know. Then the triangle inequality gives you the inequalities like this and like this. Just because Cauchy-Schwarz inequality is true and the inner product is defined, so you now have lots of many interesting inequalities. That's the end of section 9.2.